mynews.studio.
Imagine this. A single plastic bottle from your recycling bin could one day be turned into a painkiller. Is it possible that what we throw away might soon fill the pharmacy shelves?
That's quite a thought. Turning waste into medicine isn't just an idea, it's already happening. And just for context, today's date is June 29th, 2025.
Yes, exactly. Just this month, researchers at the University of Edinburgh announced that they've managed to engineer E. coli bacteria to convert PET plastic, the kind used in water bottles, straight into acetaminophen, which most people know as paracetamol.
So, let me get this straight. They're using bacteria to transform plastic trash into painkillers? How do they actually do that? PET plastic isn't exactly easy to break apart.
Right, that's the tricky part. The process begins by chemically breaking PET down into its core components. This is actually a major obstacle, both from a technical and an economic perspective, since it complicates and adds cost to the entire process.
Okay, so after they have those basic components, what do they do next?
That's where the engineered E. coli come in. The bacteria are fed those molecules, and they've been given a synthetic metabolic pathway. There's a key step called the Lawson rearrangement.
Wait, Lawson rearrangement? That's usually a chemical process, isn't it? And now it's happening inside living cells?
Exactly. Inside these bacteria, that chemical reaction produces para-aminobenzoic acid, or PABA, which is then further converted, still by the bacteria, into acetaminophen.
So, in effect, the bacteria are acting as tiny chemical factories, turning waste into something useful. But how efficient is this method?
It's quite efficient. They're able to convert up to 92% of the plastic-derived input into acetaminophen. The whole process happens at room temperature, takes just 1 to 2 days, and produces almost no carbon emissions.
That sounds like a big leap forward compared to how we usually make acetaminophen, which mostly comes from fossil fuels, right?
That's right. In fact, making pharmaceuticals is even more emission-intensive than the car industry, about 55% higher, actually. So this new route could make a real difference in terms of lowering emissions.
And we can't ignore the scale of plastic waste. PET is everywhere, over 350 million tons produced every year. Most of it ends up in landfills or the ocean. Can this process really help address that issue?
In principle, yes. Rather than recycling PET into low-value products that might still end up polluting, this process upcycles the plastic into a high-value medicine. It's a true example of a circular economy where waste becomes a resource.
But scaling up from a lab to industrial production is rarely simple. What are the main challenges in making this work on a larger scale?
There are several hurdles. First, improving how PET is broken down and delivered to the bacteria. Then, scaling up the bioreactors, keeping the bacteria healthy and productive at much larger volumes isn't trivial. Plus, all of this has to be done while keeping energy use and emissions as low as possible.
And on the business side, traditional methods for making acetaminophen are already cheap and efficient. Can this new approach compete?
That's another significant challenge. Established manufacturing processes have decades of optimization and benefit from scale. This new method still needs to prove itself in terms of cost and reliability.
And then there's regulation. Medicine made by bacteria digesting plastic. That's not something regulators have seen before. How big of a hurdle is that?
It's a major one. Every part of the process, how the medicine is made, its purity, its safety, will come under close scrutiny, and public acceptance is a factor too. Even if the product is chemically identical, will people feel comfortable taking medicine made from waste plastic?
That's a fair point. Clear communication will be important. And the potential goes beyond just acetaminophen, right? Could this method be used for other drugs or chemicals from different plastics?
That's what makes this so promising. If the process can be adapted for other products, it could change how we handle both plastic waste and pharmaceutical manufacturing worldwide. But it's going to need more research, funding, and public trust.
So to sum up, We have a technological breakthrough that could tackle both plastic pollution and sustainable medicine. The science is strong, but the road ahead involves technical, economic, and social challenges. How soon before we see this in practice? And could these methods apply to other drugs?
Those are exactly the questions that will shape what comes next for this technology.
If a plastic bottle can turn into a painkiller, it does make you wonder, what else could our waste become?
Thanks for joining us as we explored a story at the intersection of science, medicine, and the environment.
Thank you for listening. This episode was produced by mynews.studio. Give it a try for free.